Welcome to this coding problem walkthrough. Today, we'll be tackling LeetCode problem number 661, titled Image Smoother. This problem involves working with 2D matrices and applying operations to calculate averages over specific regions. It's a great exercise to enhance your problem-solving skills and understand matrix traversal techniques. Let's dive in. An image smoother is a type of filter used to reduce noise within an image. In this problem, the image is represented as a 2D integer matrix called IMG, where each element corresponds to a pixel value in grayscale, ranging from 0 to 255. The objective is to calculate a new matrix where each cell contains the smoothed value of the corresponding cell in the original image. To determine this smoothed value, we consider the 3x3 grid of cells centered around the target cell, calculate the average of the pixel values within that grid, and then take the floor of the result. If any part of the 3x3 grid falls outside the boundaries of the matrix, those cells are simply ignored. The final output is a new 2D matrix that reflects these smoothed values, maintaining the same dimensions as the input matrix. Let's look at an example. Here, the input matrix IMG is a 3x3 grid where all the values are 1, except for the center cell, which is 0. The output matrix, after applying the smoothing operation, is a 3x3 grid where all the values are 0. This happens because for each cell, we calculate the average of the values in the 3x3 grid centered at that cell and then take the floor of the result. Since the values of the surrounding cells are relatively small, and because of the floor operation, all the smoothed values turn out to be 0. This demonstrates how the smoothing filter works to process the input matrix and generate a new matrix with reduced noise. To better understand the calculations, let's break it down for specific cells. For the top left cell at position 0, 0, the 3x3 grid includes cells 0, 0, 0, 1, 1, 0, 1, 1, with values 1, 1, 1, 0. The average is calculated as the sum of these values, which is 3, divided by the number of cells, 4. Applying the floor operation gives a smoothed value of 0. For the center cell at position 1, 1, the 3x3 grid includes all 9 cells of the matrix, with values 1, 1, 1, 1, 0, 1, 1, 1, 1. The sum of these values is 8, and dividing by 9 gives an average of approximately 0.89, which floors to 0. Similarly, the smoothed value for every other cell in this example is also 0, resulting in the final output matrix. Now, let's consider another example with a different input matrix. Here, the values in the matrix are more varied. For the top left cell at position 0, 0, the 3x3 grid includes cells 0, 0, 0, 1, 1, 0, 1, 1, with values 100, 200, 250. The sum of these values is 550, and dividing by 4 gives an average of 137.5, which floors to 137. For the center cell at position 1, 1, the 3x3 grid includes all 9 cells in the matrix, with values 100, 200, 100, 250, 200, 100, 200, 100. The sum of these values is 1050, and dividing by 9 gives an average of 116.67, which floors to 138. By applying similar calculations to the other cells, we generate the output matrix, which is smoother but retains the overall structure of the input image. Finally, let's address some edge cases. If the input matrix contains only a single cell, such as IMG equals 5, there are no neighboring cells to consider, so the smoothed value is simply the value of that single cell, resulting in an output of 5. For a single row matrix like IMG equals 1, 2, 3, the smoothing operation considers only the neighboring cells along the row. For instance, the smoothed value for the cell at 0, 1 is the average of 1, 2, 3, which floors to 2. Similarly, for a single column matrix like IMG equals 1, 2, 3, the smoothing operation considers only the neighboring cells along the column. These edge cases demonstrate how the algorithm adapts to different matrix dimensions while maintaining the same smoothing logic. To begin solving the image smoother problem, we start by discussing the brute force approach. The main idea here is to iterate through every cell in the given 2D matrix and calculate the average of all valid neighbors, including the cell itself. A valid neighbor is any cell that lies within the bounds of the matrix. For each cell, we look at its 3x3 neighborhood, sum up the values of all valid cells, count them, and then compute their average. It's important to note that each cell can have a maximum of 9 neighbors, this includes itself and up to 8 surrounding cells. However, cells on the boundary or at the corners will have fewer neighbors, so we need to add special checks to ensure the indices don't go out of bounds. Using nested loops to traverse through the 3x3 grid for each cell makes this process straightforward. In terms of complexity, the time complexity is O(m*n), as we process each cell in the matrix, and the space complexity is also O(m*n), which accounts for the output matrix where the results are stored. Now, to make the process more efficient and modular, we can consider an optimized approach using delta offsets. Instead of manually checking the boundaries for each neighbor, we define a list of 8 delta offsets to represent all possible directions a neighbor can be located relative to the current cell. For instance, the delta 1, 0 moves one step down, while -1, 0 moves one step up, and so on. By centralizing the neighbor traversal logic with these deltas, we simplify the process and avoid hard-coding specific boundary checks. Although we still need to verify that the resulting indices for each neighbor are valid and within bounds, this approach significantly cleans up the code. The computational complexity remains the same as the brute force approach, with O(m*n) time complexity and O(m*n) space complexity for the output matrix. However, the delta offset method makes the implementation more structured and easier to maintain. Given the two approaches, we chose the optimized method with delta offsets as our strategy to solve the problem. While the brute force approach is simpler to implement, it involves repetitive boundary checks and hard-coded logic for neighbor traversal. In contrast, the delta offset method centralizes this logic, making the code cleaner, less redundant, and easier to debug. This modularity not only improves clarity but also reduces the likelihood of errors in future modifications. In terms of trade-offs, both approaches share the same time complexity of O(m*n) and are computationally feasible given the problem constraints. Since the matrix size is generally small and each cell has at most 9 neighbors, the computational costs are acceptable. Ultimately, the delta offset approach stands out for its readability and maintainability, which is why it is the preferred solution. The goal of this problem is to compute a smooth version of a given 2D matrix, where each cell in the output matrix is the average of all valid neighbors of the corresponding cell in the input matrix. A neighbor is considered valid if it lies within the bounds of the matrix, and this includes the cell itself. The smoothed matrix will have the same dimensions as the input matrix. To achieve this, we start by initializing a new matrix, smoothed, with the same dimensions as the input matrix, but filled with zeros. This will be the output matrix where we store the computed averages. Next, we define the relative directions that represent all possible neighbors of a cell, including the cell itself. These directions are given as pairs of row and column offsets, like -1, -1 for the top left neighbor and 1, 1 for the bottom right neighbor. Finally, we iterate over each cell in the input matrix using nested loops, one for the rows and another for the columns, so that we can process every cell individually. For each cell in the input matrix, we now focus on collecting its valid neighbors. We start by initializing 2 variables, sum_neighbors to keep track of the sum of all valid neighbor values and count_neighbors to count how many valid neighbors there are. Using the list of neighbor directions, we calculate the coordinates of each potential neighbor by applying the direction offsets to the current cell's coordinates. Before accessing a neighbor, we check if its coordinates are within the valid bounds of the matrix. If a neighbor is valid, we add its value to sum_neighbors and increment count_neighbors. After processing all possible neighbors, we calculate the smoothed value for the current cell by performing integer division, sum_neighbors divided by count_neighbors. This ensures the result remains an integer, which is important for the output. Once all cells in the matrix are processed, the smoothed matrix is returned as the final result. Key insights include handling edge cases like cells on the edges or corners, which have fewer neighbors, and ensuring that we return an empty matrix immediately if the input matrix is empty. This algorithm is efficient because for each cell, we iterate through at most 9 neighbors, resulting in a time complexity of O(m*n), where m and n are the dimensions of the matrix. The memory usage is also O(m*n) to store the smoothed matrix. Integer division plays a key role here since the average of pixel values must remain an integer in many image processing scenarios. Regarding data structures, we use the input matrix img to store the original pixel values, which can be accessed in constant time for each neighbor. The result matrix, smoothed, is updated cell by cell during the computation and returned as the final output. We also use a direction list, which is a simple list of tuples representing relative directions to find neighbors. This allows us to traverse neighbors concisely without hard-coding each condition. To better understand the process, consider an example input matrix where each pixel value is either 1 or 0. Let's walk through the computation for the cell at position 1, 1 in the matrix. The possible neighbor directions include all combinations of row and column offsets within a 3x3 grid centered around the cell. The valid neighbors for this cell are those that fall within the bounds of the matrix, such as 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, and 2, 2. The values at these positions are 1, 1, 1, 1, 0, 1, 1, 1, and 1. Summing these values gives sum underscore neighbors equals 9, and the total number of valid neighbors is count underscore neighbors equals 9. Using integer division, we calculate the smoothed value for this cell as 9 //9 equals 1. The result matrix, smoothed, is updated accordingly, with this value stored at position 1, 1. After processing all cells, the final smoothed matrix is returned, where the computed values reflect the average of valid neighbors for each cell. This code solves the image smoother problem, number 661, on LeetCode, where the goal is to calculate a smooth version of a 2D matrix by averaging the values of each cell and its neighbors. Here's a step-by-step breakdown of the implementation. 1. Input and initialization. The function begins by determining the dimensions of the input matrix img, denoted by m and n. A new matrix result is created with the same dimensions as the input matrix, initialized to zeros. 2. Neighbor directions. To simplify the traversal of neighboring cells, a directions list is defined. This list contains relative offsets for all 8 possible neighbors and the cell itself. 3. Outer loop, matrix cells. The function iterates over each cell in the input matrix using nested loops. The outer loop iterates through the rows, I, and the inner loop iterates through the columns, j. For inner loop, neighbor traversal, for each cell, I, j, the function initializes total, to sum up the values of the neighbors, and count, to count the valid neighbors. It then loops over all 9 potential neighbors, based on the directions list. 5. Boundary check. For each neighbor, NI, New Jersey, the function checks whether the neighbor is within the bounds of the matrix. If it is, the value of the neighbor is added to total, and count is increment. 6. Compute average. After processing all valid neighbors, the average is calculated as the integer division of total by count. This value is assigned to the corresponding cell in the result matrix. 7. Return result. Once all cells have been processed, the result matrix containing the smoothed values is returned. ### key points. The directions list simplifies the neighbor traversal by encapsulating all possible relative offsets. The boundary check, 0 equals NIM and 0 equals New Jersey N, ensures that only valid neighbors are included in the computation. The algorithm has a time complexity of O, m*n, where m and n are the dimensions of the input matrix. This is because each cell and its neighbors are processed in constant time. This implementation is efficient and handles edge cases, such as cells on the matrix boundaries, seamlessly. Here, we begin by defining the class solution and the method image_smoother, which takes a 2D integer array img as input and returns a new 2D array representing the smoothed image. First, we extract the dimensions of the input matrix, m for the number of rows and n for the number of columns. We also initialize a new 2D array result with the same dimensions to store the smoothed pixel values. Next, we define an array directions that contains offsets for all 8 possible neighbors of a cell, as well as the cell itself. These offsets will help us traverse the surrounding cells during the computation. We then begin iterating through each cell in the matrix using 2 nested loops, where I represents the row index and j represents the column index. For each cell, we initialize 2 variables, total, to keep track of the sum of valid neighbor values, and count, to count how many neighbors are included. Now, for each cell, we iterate through the directions array to calculate the coordinates of its neighbors. Using these offsets, we determine the row and column indices of a potential neighbor as NI and New Jersey. Before processing the neighbor, we check if it falls within the bounds of the matrix, ensuring the indices are valid. If the neighbor is valid, we add its value to total and increment count by 1. After processing all valid neighbors for a specific cell, we compute the average by dividing the total by count. This average value is then stored in the corresponding position in the result matrix. Once all cells in the input matrix have been processed, the result matrix will contain the smoothed values for every pixel. Finally, we return the result array, completing the implementation. This approach ensures that each pixel in the output matrix is the average of its own value and the values of its valid neighbors, providing a smooth representation of the image. To begin solving the image smoother problem, let's consider a simple example with a 3x3 matrix. The input matrix consists of integers, and our goal is to compute a smooth version of this image by averaging the values of each cell and its neighbors. First, we initialize the necessary variables. The dimensions of the matrix are m equals 3 and n equals 3. We also create a result matrix of the same size, filled with zeros, which will hold our smooth values. Additionally, we define a directions array to represent all possible neighbor offsets, including the cell itself. These directions will help us efficiently calculate the sum of a cell's neighbors. Now, let's process the top left cell, 0, 0. We initialize total to 0, which will store the sum of the cell and its valid neighbors, and count to 0, which will track how many neighbors contribute to the sum. Checking each direction, the valid neighbors 4, 0, 0, are 0, 0, 0, 1, 1, 0, and 1, 1. Adding their values, we calculate the sum as 1 plus 1 plus 1 plus 0 equals 3, and the count becomes 4. Finally, we compute the smoothed value for this cell as the floor division 3//4, which equals 0. This value is stored in result 0, 0. Next, we process cell 0, 1. Similar to the previous cell, we start by initializing total to 0 and count to 0. Checking its neighbors across all directions, the valid ones are 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2. Summing their values gives us 1 plus 1 plus 1 plus 1 plus 0 plus 1 equals 5, and the count is 6, as there are 6 valid neighbors. The smooth value for this cell is calculated as 5//6, which equals 0. This result is then stored in result 0, 1. The process continues similarly for the remaining cells in the matrix. For each cell, we iterate over its neighbors, check their validity, calculate the sum of their values, count the number of valid neighbors, and compute the smoothed value using integer division. This ensures that every cell in the result matrix contains the averaged value of its corresponding cell and surrounding neighbors, adhering to the problem's requirements. To understand the time complexity of the solution, we start by analyzing its structure. The algorithm uses 2 nested loops to iterate over every cell in the input image. If the image dimensions are m by n, this results in m*n iterations in total. For each cell, I, j, the algorithm examines up to 9 neighboring cells, including the cell itself. This is a constant number of operations because the number of neighbors does not depend on the size of the image. Additionally, for each potential neighbor, the algorithm performs a bounds check to ensure the indices are valid. This involves a fixed number of operations for each neighbor. Finally, operations like summing the values of valid neighbors and counting them are also constant time operations per neighbor. Together, these steps form the basis of the time complexity analysis. Now, combining these individual components, we can determine the total time complexity. Since the algorithm performs constant work for each cell, processing up to 9 neighbors and performing arithmetic operations, the work per cell is O(1). Given that there are m*n cells in the image, the total work across all cells results in a time complexity of O(m*n). This remains true for all cases best, average, and worst, because every cell is processed and its neighbors are checked regardless of the input. The algorithm's efficiency comes from the fact that it scales linearly with the size of the image. Next, let's analyze the space complexity of the solution. The algorithm creates a new output matrix result with the same dimensions as the input image, which requires O(m*n) space. Beyond this, there is a fixed list of directions with 9 tuples, representing the relative positions of potential neighbors. As the size of this list does not depend on the input dimensions, it requires only O1 space. Additionally, the algorithm uses scalar variables such as total, count, and the indices for iteration, all of which also require constant space. Finally, the input matrix IMG is provided and does not contribute to additional space usage, as the algorithm does not create a duplicate of it. Combining these factors, the dominant space usage comes from the result matrix, leading to an overall space complexity of O(m*n). Comparing this to a brute force approach, the current solution can be considered a direct, brute force method because it iterates through each cell and its neighbors explicitly. However, since the number of neighbors is limited to a constant maximum of 9, the algorithm remains efficient for this problem. While minor optimizations could reduce constant factors such as avoiding unnecessary checks for neighbors at the edges, these would not affect the asymptotic complexity, which would still be O(m*n). Finally, let's summarize the mathematical justification for the big O analysis. The outer nested loops iterate exactly m*n times, contributing O(m*n) to the total complexity. For each cell, processing up to 9 neighbors involves constant work per cell, or O(1). When multiplied by the total number of cells, this also results in O(m*n). Therefore, the overall time complexity is O(m*n). Similarly, the primary space requirement comes from the result matrix, leading to a space complexity of O(m*n). In all cases best, average, and worst, the algorithm's time complexity remains consistent at O(m*n). Given the problem constraints, the solution is already optimal in terms of asymptotic complexity, and further refinements would only impact constant factors without changing the big O classification. One common mistake when solving the image smoother problem is not handling edge cases properly. For example, boundary cells like the top left, top right, bottom left, and bottom right corners of the matrix have fewer neighbors compared to cells in the middle. Failing to account for this can lead to errors because you might attempt to access out-of-bound indices. This brings us to another mistake, accessing out-of-bounds indices. This often occurs when using hard-coded ranges or incorrect loop conditions that don't check if a neighboring cell is within the matrix dimensions. Such an oversight can result in runtime errors during traversal. Lastly, integer division can also trip people up. In languages like Python or C++, using integer division, such as some // count, might introduce rounding errors, especially if the problem expects floating point results. This can lead to incorrect outputs, as precision is often crucial when calculating averages. Always ensure you're using the correct division type based on the expected output format. Another mistake to watch out for is using inefficient nested loops, especially when working with large matrices. A brute force approach that processes every cell and its neighbors with multiple nested loops can lead to a time complexity of O(n³), or worse. This is problematic for larger test cases, as it's likely to cause time limit exceeded errors. Optimizing your approach to avoid redundant calculations is essential. Additionally, modifying the input matrix in place while iterating over it is a common pitfall. Changing values in the matrix as you traverse it can overwrite original values that may still be needed for subsequent calculations. To avoid this, you should consider using a copy of the matrix or an alternative method that ensures the integrity of the data during processing. Now, let's consider some insights for interviews. Recognizing patterns is key. This problem is often a variation of image smoothing, convolution operations, or sliding window techniques. Being able to identify these patterns can help you connect it to similar problems and optimize your solution. Interviewers may also focus on how you handle redundant calculations. For example, pre-computing row or column sums can significantly speed up the neighbor-based calculations, especially in larger matrices. They might also evaluate your attention to detail by asking how you would handle edge cases, such as boundary pixels or rows and columns along the edges. Lastly, expect to discuss trade-offs. For instance, using extra space for a copy of the matrix can make the implementation simpler, but it increases memory usage. On the other hand, performing in-place updates might save space but requires more complex logic. Related problems that can help you practice these concepts include LeetCode 304 for range sum queries, LeetCode 54 for spiral matrix traversal, and LeetCode 73 for setting matrix zeros. To approach the problem, there are several strategies you can consider. The brute force or naive method involves iterating through every cell in the matrix and calculating the average of all valid neighbors. While this is simple to implement, it can be inefficient for larger matrices due to its O(n*m*k) complexity, where k represents the average number of neighbors. A more optimized approach is to use a prefix sum matrix. By pre-computing the prefix sums, you can calculate the sum of any submatrix in constant time, reducing the overall runtime. However, this requires extra space for the prefix sum matrix, which is the trade-off. Alternatively, you can process the matrix in place with extra logic. This involves using markers or temporary values to avoid overwriting the original values during traversal. Although this saves space, it increases the complexity of implementation. Choosing the right approach depends on the constraints of the problem and the context in which you're solving it. Great job working through this problem. To summarize, we explored the image smoother problem, where we processed a 2D matrix to compute averages for each cell based on its neighbors. We discussed boundary conditions and the importance of efficient traversal. Remember to keep practicing similar problems to strengthen your skills. Thank you for watching, and don't forget to like, subscribe, and stay tuned for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!